In this video, we're going to talk about sensitivity analysis of linear programming results. And we're going to get familiar with some concepts such as shadow price, opportunity cost or reduced cost, and allowable increase or decrease for objective function coefficients and right-hand side vector. Before going through that, before actually doing one example and going through all the elements of the sensitivity analysis report that Excel provides, I just want to review this again, the linear programming solving process, and see where sensitivity analysis stands in this process. So always the first step is determining the parameters and understanding the constraints, decision variables, and the objective that we have before we can go ahead and solve the problem. We need to understand the problem and characterize all the elements that needs to come together in order for us to formulate the problem. Once we have this understanding, we can go ahead and mathematically formulate the problem. And then, depending on the tool that we're using, we need to model our problem. We need to code our problem. In Excel, we just need to create a spreadsheet model, spreadsheet setup, and then solve it. Use the solver to solve it. And at the end, most of the time, this is a very crucial part of solving process, LP solving process, the sensitivity analysis, which is basically understanding what happens to our solution, to our objective function, if any of these parameters change, if my right-hand sides change, if the amount of available resources change, if the price, if the profit per unit change, what is going to happen to my solution? What is going to happen to my objective function? So this is basically the sensitivity analysis. We want to know how sensitive our solution is with respect to the parameters in the problem, with the objective function coefficient and with the right-hand sides in the constraints, which is basically most of the time those actually characterize the amount of available resources that we have for the production or for whatever reason that we're solving an LP. So the sensitivity analysis in Excel is based on the assumption that only one piece of input data has changed. So we're going to go ahead and do one example on sensitivity analysis here, but the sensitivity analysis report that Excel provides is always with the assumption. It actually provides the classical sensitivity analysis. It's always all those results that we have, all those numbers that we have is very important to understand this assumption that those numbers are with the assumption that only one piece, only one objective function coefficient, assuming everything else is the same. If that coefficient changes, what happens to your objective function? What happens to your optimal solution? The optimal value of your decision variable. So this is really what Excel provides. Only one parameter change at a time. And then we want to see what is the impact on the solution, what is the impact on objective function, the optimal value of objective function, right? If you need to know, for example, for a problem, you want to see what happens if price increases by 5%. Price of item 1 and item 2 and item 3. If price of all of them go up by 5%. If the demand goes down by 10% at the same time. So if you have more than one parameter and you want to see what happens if all of them changes if all of them change at the same time. You can't rely on the sensitivity report that Excel provides. You need to run the problem again. You need to make those changes on your model, on your spreadsheet model, and run it again. I'll show you what I mean by that. So I'm not going to solve another problem for this sensitivity analysis. We have already solved one example, the PAR incorporation example. So we've already formulated that example, and we solved it. And we actually got the answer report, and we interpreted the answer report. But now I'm just going to go ahead and get the sensitivity report after we solve it, get the sensitivity report, and then go through the elements that the sensitivity report provides. So before doing that, let me just quickly remind you of the problem. We had two products. This is a production planning problem. We had two products, standard bags and deluxe bags. We have the profit contribution, the profit per unit of standard bags and deluxe bags. So we can write down our objective function. And then we had some operating constraints. So we had four departments that need to work in order for us to make standard and deluxe bag: cutting and dyeing, sewing, finishing, inspection, and packaging. Four departments. And for each one of them, we have limited resource. We have limited number of limited labor hour available from each one of these departments. And we cannot go beyond this. And we also have per unit of standard and deluxe bag the time that we need from each one of these departments. So we have those. Therefore, we can write down the left-hand side and then the right-hand side and form the constraint. The amount of time needed from cutting and dyeing department should not go beyond 630 hours, which is the available number of hours from this department. And same thing for the other department. If you need more on this, if you don't remember all the details, I recommend going back to this example, the simple maximization example that we have solved, and go through all the details of the problem in this slide and in the previous video. So having this formulation, having this model, spreadsheet model, I'm just gonna go ahead and use this in order for us to create a sensitivity analysis, and we're gonna go ahead and interpret the result in the sensitivity analysis. So again, I'm not gonna change anything. I just go to the solver, and by default, if you're using the same example, the same file that I'm using right now, since we've solved it before, all the solver setup should be saved by default. Like everything that we have done is in here. So I'm not gonna make any changes. The only thing that I'm gonna do is to press solve. So nothing is gonna change on my spreadsheet. Everything is perfect. The only thing is that I've already got an answer report. I'm now gonna click on sensitivity and limits report. And those are basically more statistic and more output on that helps us to interpret the answer, interpret the results, more on the sensitivity and how the decision variables and how the objective function is going to behave when we make changes. All right, okay. So it's going to add a sensitivity report and a limits report to this Excel file, right? Now I'm going to go to the sensitivity report and go through these numbers one by one and trying to define them and make sure that we understand everything that is going on in here in the sensitivity report, and then we go to the limits report. So in the sensitivity report in Excel, there are two tables, a variable cells tables and a constraints table. In the first one, we had two decision variables, right? So one for each decision variable, right? The sensitivity report is usually based on two factors, two sets of parameters. The first one is objective function coefficient. And for each decision variable, we have one objective function coefficient. So the first table is actually telling us what happens. That's the core message of the first table. What happens if these two guys, these two objective function coefficients change, any of those, all right, assuming the other one and everything else is the same. Whereas the other one is mostly with respect to the right-hand side of the constraint. What if the amount of resources that we have available in here, the amount of resources, what happens if these guys, any of those, change? Like we're talking about individual changes here, like I said, one change at a time. And what happens, like I said, in the first table, what we're talking about, these two guys, 10 and 9, what happens if these two change? And in the second table, we are talking about these right-hand side, the right-hand side vector. So here, the first table should have 2 rows. The second table should have 4 because we have 4 constraints, 2 decision variables. All right, now let's get into it. So in the variable cells, like I said, we have 1 row for each decision variable. And then it reports the objective function coefficient, which is basically what we have right now, 10 and 9 in the problem that we have solved. So this is nothing new. We already knew it. The other thing that we already knew is the final value. We already know this from the answer report. You can just check here, 540 and 252, or you can just check it here, decision variables, all right? So this is nothing new. Objective coefficient, again, objective function coefficient, 10 and 9. We already knew those guys, right? 10 and 9. Now we have allowable increase and decrease for each one of them, for each one of the objective function coefficient. And we also have something that is called reduced cost or opportunity cost. This one is a little advanced. This one is not actually in the book. I'm gonna define this one at the end after we talk about everything else. I'll get back to this one and explain it at the end. This is a little trickier than everything else that we see in this table. So let me just get to the allowable increase, allowable decrease. This defines allowable increase and allowable decrease, define the range for objective function coefficient, define the range for objective function coefficient in which or for which if objective function coefficient change, for which in case of an individual change of objective function coefficient in this range, optimal solution remains the same. So that's just the definition of this. These two, allowable increase and allowable decrease, that just defines a range for the objective function. Right now we have just two numbers, but with these we can define an interval, a range, that if this the objective function coefficient for this variable, if that makes one individual change within that range, the optimal solution, these two, 540 and 252, are not going to change. Those are going to be the same. Of course, the objective function, the optimal value of objective function is going to change. But these two, the best decision that we are going to make is not going to change. The profit is going to change, but the amount of production is not going to change. So let me first, okay, so allowable increase, let me just find the minimum and maximum, or lower bound and upper bound of this value. So 10 is current value plus minus allowable decrease. 9 minus 2.33, and max is 10 plus allowable increase, and 9 plus 5.28. So these guys define the range. So now I have the range for each objective function coefficient. Individual change within this range is not going to change the objective, is not going to change our optimal decision. How do we know that? How we can check that? So, and then remember this, the actual mean and max that I put here, they're not included. So this is very important. So you can increase 10 up to 13.5, but not 13.5. Like if you increase 10 to 13.4, the optimal solution is not going to change. So let's just try that and see if this is correct. So here I said profit per unit is 10 for standard bag and 9 for deluxe. From my sensitivity report, I know that I'm allowed to increase it all the way to 13.5, but not 13.5 itself. Anything below this, as long as it's not 13.5, that's fine. So I'm just going to change this 10 to, let's say, 13.4. All right. So of course, the objective function of the profit changes, but let's see if the optimal decision values change. So if I come to the solver and solve it again with the new profit, and this new profit is going to make some effect because we already saw that the objective function changed, right? So if I press on solve, you see the amount of production. Of course, the objective function is going to change, but the amount of production did not change. So that's a very strong statement. If you have, instead of just one value, if you have a range for any of your objective function, and you can say, if assuming everything else is going to stay the same, if I make one individual change in here, what is my maneuver range? How much I can go up, how much I can go down, and still my production plan, my production schedule is optimal. I don't need to change this. This is not sensitive to this. My production schedule is not sensitive to my to the profit per unit of standard bag, assuming that everything else is correct, as long as it stays within this range. So I just make it 10 again, just to get back to the normal, and then maybe solve it again. All right, going back here, and if, like I said, 13.5 is not included. So if I change it to 13.5, things are gonna change after we solve it. So if I solve it again, this, you see, this now standard bag is more favorable. So we put everything, all our resources toward production of standard bag. So you see that the last number, 13.5, is not actually included. So everything between these two numbers, but not themselves. So I just bring it back to the original, and then you can change, and then you can play for yourself and see how things are not sensitive or are sensitive with respect to changes in your objective function coefficient, right? So next, so this is really about it. We'll get back to the reduced cost at the end. Let me just move on to the next table, the constraint table. We have, for each constraint, we have a left-hand side and a right-hand side. The value of right-hand side, it's given. This is, it's given in our formulation. This is what we have said, or this is what we have decided and what we have provided to the solver. 630, 600, 708, 135. So this is, there's no surprise. This is what we have already know, right? Okay, so this is the right-hand side. And then this one is, so right-hand side, this one is the left-hand side. The final value of a constraint, it's talking about the value of left-hand side, which in this case, in the case of a production planning problem, this is the amount of resources that you're using, right? So when we define these constraints, we said the amount of time that you use or you need from each department cannot go over the available amount. So that's exactly what we are having here, the amount of the value of left-hand side. So from cutting and dyeing, out of 630, we are using 630. Out of 600 of sewing time, we are using 480. So this is not binding. You can say from here that this is not binding. Why? Because we're not using everything, all the resource that we have available, right? And this is not binding. And then this one is binding. Everything that we have available, we're using. This one, again, is not binding. It's probably better if you don't really need to specify binding and not binding, but I'm gonna use this for, I have a point to make later when I'm talking about shadow price. All right, so that's so nothing new yet. So this was what we already had in our answer report. Here, we had the left-hand side, right? We had the left-hand side for each one of them, and then we knew whether they were binding or not binding. So there's nothing new except for this that was not provided, but we already have those in our formulation. So nothing really exciting yet. There's one piece that is extremely important for sensitivity analysis, and that is called shadow price. And let me just make it red, shadow price. Shadow price, it's the definition of shadow price is the change in, is the rate of change in objective function, the optimal value of objective function. In this case, profit, objective function is profit. Rate of change in profit with respect to your right-hand side. In other words, if you increase the current right-hand side by 1 unit, how much your objective function, your profit, optimal profit, is going to go up, is going to improve, all right? Or is going to decrease if in case you have a negative number. So this is shadow price is range of change in optimal value of objective function with respect to 1 unit change. Again, we're always talking about individual change here. Like this one, it says optimal value of profit function is going to go up by 4.370 or 35 cents if we increase the amount of available resources from cutting and dyeing department by 1 unit. So instead of 630, if we increase it to 631, everything else the same, profit is going to go up by this much. And then you can test this. You can check that. Rate of change in optimal value of objective function with respect to 1 unit change, 1 unit increase in RHS, in the value of right-hand side. And that is the definition of shadow price. Let me just add this. And that's a very important measure. That's a very important factor for us when we are deciding if, let's say, if we have this schedule right now, and if we get one additional person that can work, or if we get some money and we can invest in either of these 4 departments, the decision to make when you want to pick the right department to invest your new labor or your new machine, when you want to increase the capacity, you want to see which one has more effect on your profit. And this is where you can come and check shadow price. So whichever, if you have the option to increase the capacity by 1 hour, which one should be? Of course, the finishing. This is the bottleneck. 1 hour extra on this is going to make you almost $7 additional dollars. So this should be your first choice, second choice, and then you never want to increase. As long as you have 2 bottlenecks, you're not going to increase the capacity on sewing and inspection, because the shadow price for those is 0, right? And then you can see here, they're not binding. Binding, it's a typo here. They're not binding. So shadow price is positive. It can be positive. Sometimes it's still 0 for binding constraint. But when you have not binding constraints, shadow price is always 0. Because if this is not binding, if you have right now 600 and you're using only 480, you're not going to increase your usage if instead of 600, there was 601 unit, right? So, and because of that, it's not going to, increasing 600 to 601 is not going to add to your profit in any way. So because they're not binding, they don't have any effect on your profit as long as they're not binding. As long as you have 2 more important bottlenecks, you don't, it's not really reasonable, it's not logical to add to your resources for not binding constraint, right? So that's a very important concept. The next Again, we have allowable increase and allowable decrease. That again, we will have a range for this time for the right hand side. Before we had for objective function coefficient, now we have for right hand side vector. For these values, we can build, we can establish some range, minimum and maximum again. But what are those? These are, so let me just, these guys define the range for right hand side, and inside any individual change inside these ranges will not change the shadow price. So shadow price, this is the insensitive range for the shadow price. As long as the constraint, the right-hand side stays within the range, within the allowable range, the shadow price is not going to change. The shadow price is going to stay the same. So let me just do the same thing, minimum and maximum for the right-hand side, right? So we have, yes, we have, and then this is infinity. This is an infinite number, right? So this is a very, very large number. So it's unbounded. And this one, the range for the right-hand side of the second one. The shadow price is not gonna change. The shadow price is gonna be zero, of course. So we just said shadow price is gonna be zero even if you increase this 1 unit, even if you increase it 600 unit, even if you increase it 1 million unit. There's no additional value on your objective function, on your profit. It's not going to make you any money, given all these assumptions that we have in our model, right? Same thing for the other non-binding constraint. So the maximum, the upper bound of the range is infinity. So this is really what it means. And then you can just check that. So if you go back and instead of 600, if you change it to 601 and run and solve it again, see, your objective function is not going to change. And in this case, your decision variables are not changing as well, right? Okay, so, and let me just bring it back to 600. So for non-binding, they're not going to change. For this one, that is a binding constraint, we just said that the objective function is going to go up by this much, 400, 4.37. So let me just copy it here. So we expect our new objective function, if I change this from 630 to 631, I expect my objective function to be this much. Let me just record this number. I just recorded the number. This, the optimal value, original optimal value of objective function plus the expected increase. If I increase this from 600 to 600 and 630 to 631, let's see. Now I want to solve. I just made that change and I just want to solve. Okay. As you can see, my optimal decision change. So the production schedule is now updated, but you see the impact on the profit. That 4.375, that is here. And this is exactly as we anticipated in our based on our solver. So let me just bring back everything to where it was. Okay, all right. So let me get rid of this. I just wanted to show you how we get those. Just wanted to test to see if they're correct. And again, you can just change that. You can, instead of 630, you can put 650 and solve the model again and check the shadow price. All right. And check the shadow price is not going to change. But this has another important implication for us. We say, okay, so you have, let's say, you have, I said, if you have 1 hour to increase, which one of these four you're going to go with? You said this one, right? But then if I tell you you have 100 hours to increase, now which one of these four you guys are going to go with? If I tell you you have the option to add 100 units to this one, you're not going to increase 100 units. You should not increase because the allowable increase is 52. You can take it up to 682.36. So that value, the shadow price, the impact of shadow price is only for up to this point. After this point, you need to reevaluate the situation again. You need to get the shadow price and then make the decision. By the way, if we wanted to add, we always should go with the finishing. Sorry if I made that mistake. We always should go with the finishing because the shadow price of finishing is higher than the cutting end. So if we get the 100 units, we come here, and of course it's within the allowable increase range, so we should add that. But what if we had 200 now, 200 hours, and we wanted to add to our right hand side? If we had 200 hours, additional hours that can be added to our RHS, we need to evaluate them based on the profit. And we see that currently, if we just want to make an individual change on our right hand side, the best one is finishing. But then, and every additional hour is going to save us, is going to bring us $6.993 additional profit, but up to 192 hours we're allowed to add. This value is only valid if we add up to this point. After that, again, we need to reevaluate and make the right decision after that, right? All right. So that's really about it. That's really about the shadow price, allowable increase, decrease, objective function, allowable increase and decrease. We have one more thing here, the reduced cost. Reduced cost, like I said, it's a little tricky. It's in general the cost or benefit of an additional production of one unit of each one of these products, right? So an additional production of standard bag, how much benefit, net benefit it's going to have for us. It's here. Or how much hidden cost or opportunity cost it's going to have for us. It's here. Right now, everything is in balance. So this is really not a good example to talk about this one. Everything is in balance. So any additional, there is no opportunity cost. You're not missing on any of those. So that's just one way of defining reduced cost. But then let me just write down maybe another way real quick. Reduced cost. That's just the change in Z star, and Z star, I mean optimal value of objective function, the profit here, optimal profit. If X greater than or equal 1 is imposed, rather than, instead of, or rather than. x greater than or equal to 0. So instead of, we had a non-negativity constraint here, right? Non-negativity constraint. We had s greater than or equal to 0. What if we had s greater than or equal to 1? All right, that would tell you if you push the production to take positive value, how much change, I mean, it can be improvement or it can be reduction. It can be good or bad on your profit. How much cost is going to decrease. So that's basically the way it's defined, or how much profit you're going to lose, how much profit you're going to make, depending on the case, depending on the value. Change in Z star, optimal profit, if instead of X greater than or equal to 0, you push it to take 1. You push it to take positive numbers. Or in other words, this is the amount of improvement in objective function coefficient that the amount of improvement in objective function coefficient before it would be possible for that variable to become, would be possible for that variable, for the corresponding variable that we're talking about, to take or to assume positive values. Positive values in the optimal solution, in optimality, in the optimal, the amount of improvement that you need to make in objective function coefficient. I mean, if you're talking about this one, objective function of standard bag is right now 10. The amount of improvement you need to make, so in this case, this is a maximization. This is positive. This means that you, the amount of increase on the objective function coefficient before you make this value, before it's reasonable for this value to become positive. It's now 10, so that's fine. There is no need to increase. Like I said, there is a balance here. Everything is in balance, so the reduced cost is 0. This is, like I said, a little trickier, but it's a very important, again, it's a very important factor for when deciding about additional production of and pushing your production to take higher values. All right. Next, we have the limits report, which is a pretty brief report, and it just has it just defines the limit, the feasibility region, the feasibility limits on the decision variables. That's all it does. So first, this is nothing. Objective name and the value of objective function, the optimal value of objective function. So we already knew it. We have seen it multiple times in answer sensitivity, in answer and in answer report, actually, right? 70, yes, we had it here. Not on this one, but we had it here. And so nothing new yet. But here, and then for each decision variable, we have their current value, the optimal value, right? The optimal value of the decision variable. Again, this is not new. We have it. We have them here. We have them in our answer report. We have them on our answer report. So again, nothing new. The new thing is this, the lower limit and upper limit for this one. Assuming the other variable and the other variables stay the same, what would be the feasible range for this production of standard bag? So if we are producing 252 units of deluxe bags, it is feasible to produce any number between 0 and 540. It is doable with the resources that we have. we can produce any number between 0 and 540. So it defines the range, the feasible range for each decision variable, assuming all other variables are in the optimality, or all other variables take the optimal values, take their optimal values. All right. Defines the feasible range for each decision variable, assuming all other variables take their optimal values. So assuming this one takes 252, you can increase, you can have the production of standard bags between 0 and 540. Any number in this range is still feasible, and then it gives you the optimal, the objective, the value of your objective function. If you have, let's say here, if you, instead of 540, if you go with 0 standard bags, that's still feasible, but then your profit will be 2268. Let's just test that. 2266. 0 for a standard bag. 2268. You can see it here. And then you can go all the way to 540, and then the optimal value is 540. So that's what we get from the limits report. This is usually the least important one, because at the end of the day, the most important thing that we get from this, this is the answer report.